Welcome! This video focuses on some of the hidden details of working with arrays. So, an array, just to review quickly what's in the book, is a collection of items. It's always the same type of item, so we can have an array of integers or an array of doubles or an array of strings, but each element, each thing in the array always has to be the same type. And it's always got to be a fixed size. We have to know that size when we compile. The elements, the values, are numbered. That number is called the index, and it starts from 0. So if I have an array of 9 things, the elements will be numbered 0 through 8. We can quickly initialize an array with a list of values with curly braces around it. If we don't initialize an array, just like anything else, it starts with random garbage. So it's always a good idea to initialize. For something like this says create me a array with 10 elements of integers. I'm going to call it list and use 8, 5, and 12 as initial values. So I'm only specifying 3 of the 10 values. When I do something like that, and so here's a similar idea. I've got an array called values of doubles. It's got 6 things in it, so 6 slots, 6 elements, and I'm saying to initialize with these 2 values. If I put in a breakpoint and build this quickly and then run it with the debugger, when I get to right here, I can see over in the debugger that in the watch window that values is got this weird value. That's actually the memory address of the array, and we'll come back to that. But I can see that the type is an array of 6 doubles, and if I crack it open, I can see the values that are there. There are the 2 values that I initialized it with, so those become the first 2 values, and anything else gets initialized to 0, anything that I didn't bother specifying, as long as I initialize at least one piece. So a handy trick to remember, if you want to start off an array and just blank it out with all zeros, just initialize the first element to 0, and everything else will automatically become 0 as well. This is critical to remember that an array has to be a constant size. We can't have a variable. It's okay to have a constant, so I can say nums and have a constant literal integer like 100, or I can have a constant declared constant like num students, that's 20, and use that to create my array. Or I can even have some expression that's guaranteed to evaluate to constant and is known at compile time. This is a constant 20, 20 plus 1 is 21, that will work fine. What doesn't work fine is having a plain variable and creating an array based on that size. Now, for why this doesn't work in C++, we've got to go talk about the stack. So hopefully you remember that C++, when we're working with variables, we are kind of allocating them on what's called the stack in memory. So if I have this chunk of code and main starts running and it throws X into memory and uses the first chunk available and takes 4 bytes because it's an integer, and then this double would take 8 bytes, and so it might end up there. And then we call foo function, and foo has this parameter q, which is an int, so it takes up 4 bytes. And then maybe it uses a char, which is 1 byte, and so it takes up that memory. And then we return from the function, and as we unwind, we just kind of stop using that memory. We give it back so that we can make use of it again when we get to something like, okay, now it's time to store z. We have a place to store it. And then as we continue on and we finish up main, the whole stack goes away. We're done with all those variables and we can kind of release that memory. So this is an efficient way to kind of keep reusing space for all those temporary variables that are created as our code is running. The only problem is to do this well, to kind of lay this out, we need to know how big each thing is, so how much space it's going to take on the stack, and we can't change those sizes once they're there. And I can't go easily change the size of y because z and x are stacked on either side of it. So what does this have to do with arrays? Well, an array is implemented with sequential blocks of memory cells. So if I have an array called quiz and it's got 3 elements that are all integers, it would be stored like this. 3 consecutive integer-sized blocks of memory where the 3 elements are stored, the 10, 5, and 8. Now, nothing is going to sanity check the indexes you use to try and access these elements. So here's a sample program. We declare an array called nums with 5 elements that are integers, and then a variable x that's set to 10. I print out x, I set nums sub 5 to 15, and then I print out x again. And you can see first time prints out x, I get 10, and then I print out x and I get 15, which is kind of odd. I didn't change x here, I tried to change the array. Well, behind the scenes, what's happened with my array, if it's got 5 elements, it really only has 4 slots 0 through 4. What this looks like in memory is something like this. Num 0, nums 1, nums 2, nums 3, nums 4, and then after that was placed the x. So if I go access element number 5 of nums, something outside the actual boundary of my array, well, C++ is happy to try and take me there and go access what would be the next thing in the array, which is actually x. And so we're actually changing the value of x to be 15, so that when we go print it out, that's why we see 15. We've walked off the end of the array. There's no warnings, no errors. We just start working with parts of memory that aren't really part of the array. Now, if you go too far out of bounds, like if I try and go 500 elements deep into the array, I'm going to leave the memory that my program is allowed to work with, and the operating system in that case, Windows, is going to step in and blow up my program, and I'll get a system level error telling me my program's been killed because it was doing bad things. But nothing about C++ is going to stop you from trying to access bad pieces of memory. So you have to be very, very, very careful that you don't walk off the end of your array. If you've got 5 elements, you only ever access 0 through 4. You don't go negative, and you don't go to 5 or beyond. Now, the other kind of important thing to realize about arrays is that there are no aggregate operations. There's no way to take a whole array like this 10, 12, 16, 31, 22 that's called nums and copy it to this other array all at once. I can't assign to other nums. I can't try and change every element to 10 like this. That doesn't work. I'm not allowed to take one array and say copy it to another one. Basically, if you want to work with an array, you have to work with one element at a time and do it to each element. So if I want to set every element to 10, I have to loop through the whole array and set each piece one by one to 10. If I want to copy an array, I'd have to go through piece by piece to the original one and copy each value to the new one. This also means that if you try and do something like print an array, what you're going to get is a bizarre result. It's not going to printing nums is not going to print the list of numbers in the array. It's going to print the memory address, that memory address that we saw in Qt Creator, which is called the base address. Anytime you talk about just an array and you don't specify num sub 0 or sub 1, you don't specify an index, when you just use the name of the array, you're really talking about the base address, which essentially is the memory address where the array starts. And so that's what, when we see this is basically telling us, okay, here's the memory address where the array starts. Given the base address, and if we know how big each element is, which we do if we know it's an int or a double, then we can rapidly calculate where a particular element is. All right, so if I know I'm looking for the third element, and I know each element, because they're ints, is 4 bytes, I can do 3 times 4 is 12, add that to the base address, and tells me 1012, that's right where I can find element number 3. So arrays we can instantly access kind of any element by basically calculating where it starts in memory.